So today we're going to get started talking about NMR spectroscopy. We've already covered infrared spectroscopy. NMR is what comes next. NMR spectroscopy presents graphs, charts, spectra that look like these down here, and so we're going to talk about all the details of those spectra today. But first, you say, I want to be a doctor. I'm planning to go to med school, and med school says I have to take organic chemistry. Why is anything we've learned so far relevant to being a doctor, being a physician? Well, one thing is very relevant to NMR, that's MRI imaging. The truth is NMR is the same technology that's used in an MRI. The interpretation results look different. You get results that look like this thing instead of that thing, but it's really just processing the data that converts something like this into something like that. In an MRI instrument, a patient is slid into a big magnet thing. In an NMR instrument, a small sample is slid into a tube between a big magnet thing. The process is the same. The sample size is different, a person versus a tiny tube, and the way the results are processed is a bit different, but all of the way that it works is the same. The truth is, the only reason it's called MRI instead of NMR is because long ago when it was invented, they were worried that people would be afraid of the word nuclear and entering this nuclear tube, because nuclear magnetic resonance spectroscopy is what NMR stands for. So like I said before, we've got this tube that's got our sample in it. Your sample is usually dissolved in a liquid, entered into this magnet, and then the magnet turns on. It pulses energy to your sample, and your sample responds in differing ways, and then all of that is sent to a computer which processes the signal and gets us these fancy little charts, these fancy little spectra. So NMR, what we are going to use it for is to identify the carbon-carbon and carbon-hydrogen framework of an organic compound. So we're going to look at the spectra and determine what is the molecule that we took a spectra of. The way NMR works is that nuclei, atoms that have an odd number of protons and odd number of neutrons, that's these as some examples, can be studied by NMR. There are more than just those, but those are the ones of interest to organic chemists. We're going to focus on carbon and proton NMR. Note this is carbon-13 because you've got to have an odd number of protons and neutrons in order to get a signal. Carbon-12 does not provide a signal that can be read by an NMR instrument. So we're breezing through the theory quickly, but the way it works is you have electrons all in various orientations in a molecule, and then you apply a magnetic field to them. Maybe you've had physics already, but when you apply a magnetic field to a negatively charged thing, it can align with the field. Here's the field, the magnetic field, external magnetic field. It can align with the field, like these alpha spin states, or it can align against the field, like these beta spin states. And there's an energy gap between those two states, and we interpret things based on that energy gap. Okay, this number is the size of the magnetic field that you're applying, the size of the external magnetic field. When you have a bigger external magnet, the gap between alpha and beta spin states is larger, and that leads to actually more clear spectra. Let me show you. So this top one was taken with a 60 megahertz NMR and 60 megahertz external magnet. This bottom one was taken with a 300 megahertz external magnet. You don't know all the details of NMR yet, so you may not be able to tell, but this top thing, it shows me a lot of peaks, a lot of jumble, but this one down here is very clear, very precise. I can very distinctly count the number of peaks in this little huddle right here. It looks like this huddle has 4, but in this instrument I can tell that it's 6 instead of 4. And that's actually important to us to be able to accurately count how many peaks are within a signal. So the bigger the magnet, the more clear the spectrum. That was a super brief introduction to how it works, but let's get down to the details that we expect you to know and be able to interpret in this class. First of all, I want to point out that the scale along the bottom is in ppm. That's parts per million. We'll talk about that in a moment. But we start out with 0 on the right-hand side of the spectrum, and the numbers get bigger as you go left. That's not in alignment with normal geometry scales of the way that a number line works, so I want to point that out. That shift along the bottom, or that number along the bottom, is called the chemical shift. That chemical shift tells us how far the signal in our compound is from a reference compound's signal. The reference compound that we use throughout almost all of organic is TMS, tetramethylsilane. The reason we choose that is we have designated that TMS has a peak that appears at 0 ppm. So we ignore a peak at 0 ppm because that's what's called our internal standard. That signal does not matter. That's just a point of reference for all of our other signals. So delta, that's a lowercase delta, is called the chemical shift. We'll talk about shift this and shift that. We're talking about the numbers along the x-axis every time we say that. There's how it's actually calculated, but we won't do calculations with them. So I said we have an external magnet that pulses to send energy to our molecule. Our molecule gets excited. The electrons in our molecule align with the magnetic field or against the magnetic field, and then they respond based on whether they're aligned with or aligned against. So even though the external magnet is, let's say, 300 megahertz, when that pulse is sent out and received by your molecule, every aspect of that molecule does not experience the same magnetic field. Even though it's a 300 megahertz, not all of them feel a 300 megahertz pulse. It all depends on the kind of environment that they're in. Protons that are considered shielded, that means there's a lot of electron density around them. Protons that are shielded, they're shielded from the full 300 megahertz pulse, so they appear what we call upfield. The opposite is true for deshielded nuclei. They're exposed. Those are downfield. Okay, this is really confusing. Wrap it up here. One more thing about the terminology. Things that are downfield, we say have a high frequency. They have large shift values. That means big numbers in their shift values. They're called deshielded. Protons that come in electron-poor environments are deshielded. Protons in electron-rich environments are shielded. They are upfield. They have low shift values, low frequency. So those columns of words all mean variations of the same thing for us to say, is it further left or further right on an NMR spectrum? We're going to use a very simple rule that is too simplified at times that says the closer you are to something electronegative, the further downfield you shift, the further left on the spectrum you go. We'll explain that better as we walk through examples in a moment, but that's sort of a summary of what NMR is and stuff like that. Let's go to what we do with it. So we're going to start out talking about carbon NMR specifically. Remember I said it's carbon-13 NMR because carbon-12 cannot be observed in an NMR spectrum. All right, let's get down to business to answer, are these chemically equivalent carbons? First of all, what does it mean to be chemically equivalent? It means in the same environment. Symmetry is something that leads to two different carbons being chemically equivalent. So we're kind of trying to detect symmetry in these examples. I think chemically equivalent will become more clear as we walk through some of these examples. If we look at our first molecule here, we've got CH3, CH2, CH2, Br. Well, I only said CH3 one time, so that leads me to say that the carbon of CH3 will show up as a unique signal. There's no other carbon that has the same sort of environment as that carbon, because that's a CH3 carbon and the others are CH2s. That's the first layer of comparison. So this CH2 will show up as an additional signal, but then I have to figure out, is this CH2 that I've put the number 2 by the same environment as this CH2 that comes next? The answer is no. The CH2 that I have given number 2 has a CH2 neighbor and a CH3 neighbor. The CH2 that I've given the number 3 to has a CH2 neighbor and a Br neighbor. They have different neighbors. That means they show up as different carbon signals because they're in different environments. Yes, this is a CH2 and so is that, but they're in distinct environments because their neighbors are different. So this carbon NMR would show me 3 signals. What about the next one? I have a CH3, CH3. Remember, we're only considering carbons because we're talking about carbon NMR. So this CH seems to be unique. Nobody else is a CH. This CH3, different from the CH, definitely. Is it the same as this other CH3? Yes, because both of those CH3s are connected to a CH that's connected to a Br. They are the same. This molecule is considered symmetric down the middle of that bond I just dashed. So that makes carbon number 2 and carbon number 2 appear as the same signal. So why did I number them carbon number 2? I'm just trying to verify, trying to label carbons that show up the same and carbons that don't. There's no significance to me giving them numbers 1, 2, and 3, or 1 and 2 in the second example. It's just I'm giving them the same number if they're chemically equivalent. Yeah? Okay. This one is different from that one, is also different from that one. This would show 3 signals because the CH2, definitely unique, no other CH2s. But this CH3 is connected to a CH2, while that CH3 is connected to an O. They have different environments, they are different signals. Both of these directly connected to an O, 1 signal. This one is different from that one, but all 3 of those around the outside that I've given number 1 are the same, but that's different from that one over there. So this one would give me 3 signals overall. Moving along, this one would show 2 signals. This would show 1, 2, 3 signals. 1. Benzene is different. Benzene is weird, but all of those are chemically equivalent carbons, aren't they? Yeah, because of resonance, they are. It's a little bit different for the next one because it's a substituted benzene. That substituent on the benzene changes things a bit. That makes this carbon unique because it's connected to the nitro. These carbons are a little bit distanced from the nitro, but still affected by the nitro. These are further distanced from the nitro, but still affected. And this one is all the way across the ring, probably still affected. This one would show me 4 signals because of symmetry down the middle of that ring. That's why those and those are the same, but 1 and 4 are different. Cool enough? Okay. So we understand chemically equivalent. What do we do with a proton decoupled carbon NMR spectrum? Well, first of all, you count the number of signals that you see. Remember, 0 ppm does not count. That's our internal standard TMS. This, around 77, there's 3 little baby bumps. Can you even see them before I pointed them out? 3 little baby bumps around 77. That's also a solvent peak. I told you our sample is typically dissolved in solvent. So the 3 little peaks at 77, ignore those. If you want to really know what they are, our solvent is CdCl3. That's chloroform, where the hydrogen has been replaced with a deuterium. Okay, good enough. What do I do with this? I see 4 signals now that I've crossed out everything that doesn't matter. Those 4 signals. All right. Well, I've got 4 carbons in my molecule. 4 signals, 4 carbons. Yeah, that's what I would have predicted, since I know that this is a spectrum of 2-butanol. If we go back to our generalized statement that's far too simplified, the further left something is on the spectrum, the closer it is to something electronegative. I can say carbon number 1 is furthest left, so I can pretty confidently say this carbon directly connected to the OH of my alcohol must be that carbon. The further left, the closer it is to something electronegative. As far as which carbons precisely are 2, 3, and 4, that's a little bit beyond our expertise and our expectations for this class, but it's totally doable in higher level chemistries. A few typed up words of things we've mostly already said. The number of signals reflects the number of different kinds of carbons in a compound. 1-butanol, nope, that was 2-butanol we just saw. 2-butanol had 4 signals because it had 4 unique carbons. It's very possible that you have a symmetric molecule, like some of the examples, and you might have 3 carbons in the molecule in total and only 2 signals. But the number of signals tells you about the number of different kinds of carbon. If the number of signals seen is smaller than the actual number of carbons in the compound, it tells you that you have some sort of symmetry within your molecule. And that fact can be used to help you come up with structures of unknown compounds, knowing whether you have symmetry or not. The chemical shift ranges over 220 ppm, starts at 0 on the left, goes to 220 on the right. That's pretty different from proton NMR, which we're going to talk about in a moment. TMS is our reference. Okay, here's a general picture of where to find certain kinds of carbons in a carbon spectrum. Do you need to memorize this picture? No, you need to know these 2 ranges. I want you to know that alkene and benzene carbons show up around or between 100 and 150 ppm. C double bond O, so that's carboxylic acids, esters, amides, all those things. C double bond O's show up between 150 to 200. They can be above 200 as well, but 150 to 200-ish. Okay, I can do that. I don't like memorizing, but I can know 2 things. Benzene carbons show up between 100 and 150. C double bond O's, 150 to 200 or so. Anything beyond 200 is definitely still a C double bond O. If you look through the textbook gives you all of this as carbon NMR stuff. If you did an internet search, you'd get even more. Do you have to memorize things like this? No way. I told you need to know benzene shows up between 100 and 150. Yeah, that's a smaller range, but 100 to 150, those are rounder numbers for me to remember. And C double bond O's show up between 150 and 200. Oh, look, sometimes they go above 200. That's okay, 150 to 200 or so. This is just a list that provides a bit more detail than the last picture, but I like the last picture because it's a broad overview. If you're ever super stuck, can you revisit this thing? Sure. But I don't think it will come to that. So as I've said, we're detecting carbon-13. Carbon-13 is not the most populous carbon isotope on the planet, so sometimes the signals are kind of small and difficult to see. The intensity of the signal can be somewhat related to the number of carbons that give that signal. However, a lot of the signals are kind of small, even if there are multiple carbons showing up under that signal. That was confusing. I'm not going to delete it. So, just because this peak is tall doesn't mean that we should assume it represents multiple carbons. It may or it may not. The only thing that I do want you to be aware of is carbons that are not attached to hydrogens often appear as very small signals in the carbon NMR. So I see 1, 2, yep, that is a signal down there, that little baby. 3, 4 signals in my NMR. This number 2 is barely peeking out of the background of my jumble down at the bottom. That number 2, that's this carbon in the center that has no hydrogens connected to it. Carbons that have no hydrogens often are very tiny signals. I can deal with that. Okay, what about proton NMR? So here's a figure from your textbook explaining chemically equivalent protons. It follows the same principles that carbon does. You're looking for protons in the same environment. Well, protons on a single carbon are in the same environment, generally. So all 3 of those are chemically equivalent. Both of those are chemically equivalent. Both of those are chemically equivalent. But these H's are not chemically equivalent to those H's, which are not chemically equivalent to those H's. Got it? That's easy to put numbers and letters on our first example here because it's what we just saw. I'm going to put A's and B's and C's on these protons. Not because that matters, but my habits, as bad as they are, I do number labeling for carbons and letter labeling for protons. I'm sorry, but you got to deal with it. It's what I do, unfortunately. This CH is different from the H3s, but those 3 H's are the same as those 3 H's. I should have said and I forgot. We would get 3 signals here, 2 signals here. 1, 2, 3 signals here. Okay, so I just feel like you're going through the same examples we just did, but what's different? Well, remember this time we're looking at protons. Check your notes. Did we have 2 signals in this carbon NMR? No, we had 3 signals in this carbon NMR and only 2 in the proton because that carbon has no protons on it. Yeah? So number of proton signals and number of carbon signals is often the same, but if you have a carbon without hydrogens or a hydrogen on a heteroatom, the hydrogen on the heteroatom will show up in the proton NMR but will not show up in the carbon. A carbon that has no hydrogens will show up in the carbon but not in the proton. Got it straight? Okay, we got more examples to do. 1 here, 2 signals. 1 here, different here, but same there, 2 signals. I just told you I do letters and then I turn that into numbers because all the benzene protons would be the same. For the same reason the carbons are the same. This and that, same. This and that, same, but different from the first. And this one is unique. 3 signals. Why did our other one show 4? Because that carbon ain't got no hydrogens. You heard me. Okay. So I've said this a time or two. The sometimes oversimplified summary. Protons and carbons near electronegative stuff is shifted further downfield. That means further to the left on the spectrum. It gives you bigger shift numbers. Okay? A nitro group, really electronegative. So the H's on the carbon next door to the nitro are pretty far downfield. The H's next door to that, still a bit further than normally predicted, but the CH3 gets kind of too far down to be greatly affected by the nitro. Same thing with a halogen next door. The more electronegative the halogen is, the further the shift value of the neighboring H's. 4.5 versus 3.5 versus 3.4 versus 3.2. Yeah, fluorine is super electronegative, so it has a dramatic impact on the neighboring hydrogens. Yeah? Okay. Here's a picture similar to the one I showed you for carbons, but this is proton stuff. Do you have to memorize these values? No, but you need to know those regions. We're going to make things even simpler, or at least I think so. We're going to say protons on benzene show up around 7. This gives a range of 6.5 to 8. Sure. I can remember one number better than 2, so I'm going to say they show up around 7. And protons on an aldehyde, you knew that's what that was, right? Right. Protons on a carboxylic acid. Those 2 types of protons show up around 10. Sure, this says 9 to 12. That's around 10. It's easier for me to remember 7 and 10 than 6.5 to 8.5, 9.0 to 12. Yeah, 2 ranges you need to know. Benzene protons show up around 7. Aromatic protons show up around 7. Aldehyde and carboxylic acid protons show up around 10. Okay, here's the more detailed version. Are you memorizing these things? No. But I do actually want to point out a thing or two here. Note, this. All of those things have this word in their ppm range. It says variable. What does that mean? Well, protons connected to heteroatoms. What is a heteroatom? Not carbon. Protons connected to heteroatoms are variable. So our summary about things closer to electronegative stuff is further left. It's great, it's well, it's good, But if you are directly connected to a heteroatom, a proton, directly connected to a heteroatom, that shifts around a little bit, and that thing about being near electronegative doesn't really apply. If you're connected to a carbon that's directly connected to a heteroatom, then you're going to be kind of far downfield. Rewind that if you need to rewind that. I'm not going to repeat it. Carbons that are CH3 carbons are called methyls. So the H's connected are called methyl protons. CH2 carbons, they have methylene protons. CH carbons have methine protons. Methine is at a higher frequency than methylene, and methylene is at a higher frequency than methyl. Okay, great. That says CH3s are going to be furthest right, CHs are going to be furthest left. That's what that means. But it really kind of depends on the environments around them as well. So don't take that as the be-all, end-all, all that you need to know. Okay. So here we're getting to the nitty-gritty details of proton NMR. Carbon NMR was simple. Proton NMR has a lot more details, and there are two main things that we will talk about in proton NMR that we did not talk about in carbon NMR. Proton NMR, you are concerned with the integration of the signals. Wait, what? Integration? This is organic chemistry. This is not calculus class. Yeah, integration. The area under the signal is proportional to the number of protons that produce that signal. So this integral has been measured at a value of 1.6. That integral has been measured and given a value of 7.0. That means 1.6 to 7 is the ratio of your integration. Okay. In this molecule, how many H's do I actually have? 11. This says that the ratio should be 1.6 to 7. But since every single proton needs to be represented on a proton NMR, I need the summation of these two integral values to equal the total number of protons in my molecule. So if the sum does not match the total number of H's, divide each number by the smallest number. So I'm going to divide by 1.6, divide by 1.6. I get 1 and 4.375. Okay, what do I do with that? Again, I need my total number of protons to equal 11. So I find a multiple that after I multiply these numbers by that number, I get a sum of 11. That's really not a great explanation, but if I multiply this number by 2 and that number by 2, I get 2 and 8.75. 8.75 can be rounded to 9. So 2 plus 9, that does represent my 11 protons. So all of that math was to say you're given integral things that really just tell you the ratio of the number of types of hydrogens you have. Sometimes you have to manipulate the actual numbers that you have to decide how many hydrogens does that signal actually represent. It represents 2 hydrogens. How many signals does that peak actually represent? It represents 9 hydrogens. The integration of a peak tells you how many hydrogens are represented by that signal. Whew, that was long. Integration is one of the major things that we talk about in proton NMR that we don't talk about in carbon, and splitting is the other thing that we will talk about in proton that we did not cover in carbon. Without simply reading to you, these things follow the n+1 rule. We'll explain with an example. The number of peaks in a signal is called the multiplicity. I much more often refer to it as the splitting of the signal, but it's officially called multiplicity. So the splitting is not the number of protons that gave you that signal. The splitting's about the number of neighboring hydrogens, the immediately adjacent. Okay. I told you we'll walk through this with an example. These hydrogens on that carbon, there are 3 of them. The number of hydrogens represented is the integration number. The number of splitting tells you about the number of neighboring hydrogens. Okay, immediately adjacent. What does it mean to be immediately adjacent? This carbon, is he directly connected to any other carbons? Nope. So that means that there are no neighboring hydrogens. 0 neighboring hydrogens means he would show up as 0 plus 1, that's the n plus 1 rule. He would show up as 1 peak. That 1 peak we give the name of singlet. It's a single little spike peak. Okay. This one. This carbon with those 2 hydrogens connected, is that carbon directly connected to any other carbons? Yes. That carbon is directly connected to this one and that one. How many hydrogens are on this one? 3 H's. How many hydrogens are on that one? 0 H's. So if I sum together those things, I have 3 hydrogens that we will call neighboring hydrogens. Who are they neighboring? They're neighboring this guy that's circled that I was talking about from the get-go. So 3 neighboring plus 1, because the rule is n plus 1, equals 4. That means 4 peaks. 4 peaks we will call a quartet. If we look at this CH3 over here, is that CH3 directly connected to any other carbons? Yeah. It's directly connected to that carbon. Does that carbon have any H's on it? Yeah, it's got 2 H's. So the number of hydrogens that are neighboring plus 1 tells me this signal should show up as 3 peaks. We're going to call 3 peaks a triplet. So I got rid of all the information except what we would call the types of peaks. Let's put together a little bit more clear picture of what this would look like. If I gave this the number A, the letter A, that means A should be a singlet. That means 1 sharp peak. The integration of A should be 3 H's. Why? Because there are actually 3 H's represented by peak A. What did being a singlet actually tell me? It told me there were 0 neighboring hydrogens, while the integration told me there were 3 hydrogens represented by that signal. B says, or B would be a quartet. A quartet looks like this. He's got 2 tall middle fingers and 2 shorter fingers on the outside. That's a quartet. That quartet should represent 2 hydrogens. The integration of peak B should be 2 hydrogens because 2 hydrogens are represented by that signal. Then why does it show up as a quartet? Because a quartet tells me I have 3 hydrogens on the neighboring carbon. Okay? Peak C. Peak C would show up as a triplet. He's got a triplet has a tall middle finger. A triplet does not tell me that 3 hydrogens are represented by that peak. A triplet tells me there are 2 hydrogens on the neighboring carbon. But the integration of that triplet would be 3 hydrogens because there are 3 hydrogens directly connected to peak C. It gets better as we go through more examples, I think. So this is Pascal's triangle. If you've never seen it, I'm sorry, that's sad. The way that Pascal's triangle works is you start out with a 1, and there are 1s all along the outside of the triangle, and you sum together the 2 numbers immediately above to get this number. So 1 plus 1 equals 2, 1 plus 2 equals 3, 2 plus 1 equals 3, 3 plus 3 equals 6. You get the pattern, yeah? That's how I was able to say that a quartet should have 2 tall middle fingers because a quartet should show that sort of ratio. I could show you a sextet would have 2 tall peaks in the middle, shorter peaks next to that, and shorter peaks outside of that. So Pascal's triangle really tells me the height of the peaks. The reason I knew a triplet had a tall middle finger is Pascal's triangle told me so. The way that Pascal's triangle comes about is all about aligning with or against the magnetic field, but you can look into all of that at your leisure if you wish. So this is an image with some fancy words, but really all it's saying is if the carbons are directly connected, these protons are considered neighbors. If they're not directly connected, the protons are not considered neighbors. And this says sometimes it's more complicated than that, but yeah. In benzene, it's often more complicated than that. We'll talk about benzene specifically in a moment. Let's put it all together in an example. I see all of these spectroscopy problems as little puzzles, kind of like a jigsaw puzzle. Most people, when they assemble a jigsaw puzzle, they put together all the exterior and then they put in the inside. What I see a table like this table at the bottom as is sort of starting to collect your edge pieces in a pile, and then we're going to sort of assemble the edge pieces, the framework, and then we'll dump in the guts. So let's start with filling out our table. So I see two signals in this NMR, and the first thing I do is label them A and B. I told you before I use letters for my proton NMR, label them A and B. And then I come down here to my table and say signal A, signal B. The next column is shift. That's chemical shift. We don't have to be super accurate, but A is around 3.5 and B is around 2.3. If we don't have to be super accurate, then why include it at all? Well, I think that it's helpful for students to start associating certain types of hydrogens with certain signal areas. It's not something I want you to memorize, but I think it's helpful to sort of write it down in the table to kind of keep your thoughts together on this kind of peak shows up in this kind of region. Okay, if you didn't notice, peak A is zoomed in over there. Peak B, or signal B, is zoomed in over there. So we could be much more accurate in our shift values, but we don't care. All right, next comes integration. Integration means trace that green line, and we see these little tiny baby green numbers. Those green numbers are the integration values. But my chemical formula tells me there are 6 hydrogens, so I need to multiply each of those integration values by 2. That means A really represents 4 hydrogens, and B really represents 2 hydrogens in order to represent all 6 hydrogens that are actually found in this molecule. The type of hydrogen, that means singlet, doublet, triplet stuff. I'm going to call A a triplet. I'm going to call B a multiplet. I like to call a quartet by its correct name, but anything 5 and above I call a multiplet because it's helpful and easy. But you could officially call this one a quintet if you wanted to. I'm going to count, and that's where I see that there are 5 peaks, so I usually put the number of peaks of the multiplet in parentheses to kind of help me keep that straight. Then comes the number of neighbors. A triplet always means that I have 2 neighboring hydrogens. A multiplet of 5 means I have 4 neighboring hydrogens. You take the number of peaks minus 1 to come up with the number of neighbors. Okay, so that's sort of putting the pile of the edge pieces together. You're taking this analogy too far, I know. Putting the pile of edge pieces together, then I start to assemble the edge pieces. I assemble the edge pieces by first looking at the integration numbers. So I see a peak that has an integration of 2. So to me that says that's a CH2. I'm going to write a B there to represent that that's the peak that has the integration of 2. Why did I put these dangly arms on the outside? Because carbon likes to make 4 bonds, and so if carbon is to make 4 bonds, a CH2 has 2 additional bonds it can make. Okay, looking at the integration of peak A integrates to 4. Can I put 4 hydrogens around a single carbon and still have a place to plug anything in? No. So an integration of 4 is most likely 2 CH2s that are chemically equivalent. So I draw my 2 CH2s and label both of those as proton A's. All right, I've almost got all my pieces. Those pieces represent all 3 hydrogens and all 6 hydrogens, all 3 carbons and all 6 hydrogens, but I have 2 BRs left over that I have not accounted for. BR likes to make 1 bond, so there are my 2 little BR pieces. That's my framework that I can build from. Now it's time to start assembling a molecule. I start assembling by looking at the number of neighbors. So I see that B is 2 H's that has 4 neighbors. Well, A actually represents 4 H's, so it must mean A and B are neighboring each other. Okay, I'm going to put B here in the middle, and I'm going to put A out on the outside connected to B. Because A's have to be chemically equivalent, that's telling me that A's are going to be a symmetric sort of molecule. The A's are going to be a symmetric piece. I don't know how to say that well. So then I can double check my coupling, my splitting. A has to have 2 neighbors. Here's A. Oh, look, 1, 2 neighbors. Here's A, 1, 2, same neighbors. B has to have 4 neighbors. Here's B, and his 4 neighbors are 1, 2, 3, 4. That's kind of cool. All of my neighboring works out. And the only thing left is my 2 BRs. Oh, look, I've got 2 holes to plug in my BRs. It's nice that I came up with a symmetric structure. I actually knew that I needed to come up with a symmetric structure because A represents too many hydrogens to be bonded to a single carbon. So this line of symmetry straight down the middle is helpful. That's why the 2 A's are in the same environment. They show up as the same peak in a proton NMR. One more thing to check before we move on to the next example. A is close to BR. What does that mean to me? It means A should be the peak that's furthest downfield. Remember, that's furthest to the right. That's the left. Furthest to the left on the proton spectrum. That was so fun. How about some more? The first thing I did was put letters on my peak sets. And I see that I've got A, B, C, D, E. Whoa, it was hard enough with 2 peaks in that last example, and now I've got 5. Yeah. We're giving a ballpark region for our shift values. A is around 5. It's not quite, but around 5. B is maybe 2.3-ish. C is maybe 1.6-ish. This D is actually zoomed in over there. D is maybe 1.2. It's actually precisely 1.2. E maybe 0.9. We're just ballparking it here, general region. If I check my integration, I've got 1, 2, 2, 6, 3. If I summed up that column, do I get 14? Yes. So I don't need to multiply by anything here. They've already been processed to be equal to the number of protons I have. Then comes type. A, I would say, is a multiplet. I think it probably looks like 1, 2, 3, 4, 5, 6, 7 peaks. And you say, what? Do those tiny babies count? They do. Remember Pascal's triangle. The taller the middle peak gets, the more squatty and tiny the peaks on the outside get. So sometimes it's very difficult to see little tiny peaks on the outside. So when you have a multiplet that you're not sure about how many it is, be a little bit flexible with the numbers. What I can know is if there's a tall middle finger, it tells me it's an odd number of peaks, because a doublet has an even top, a quartet has an even top, a sextet has an even top. What I mean by that, a triplet has a tall middle finger, a quintet has a tall middle finger. If you have an odd number of peaks, middle finger. If you have an even number of peaks, the 2 middle peaks are equally high. So peak A is either 5 or 7, but I'm going to lean towards 7 because I've done this before. So B looks like a triplet to me. C is a little bit difficult to see, but it looks like these 2 are even. And I think that I see little shoulders out there, so I'm going to say a multiplet of 6. D, that's a doublet. E, that's another triplet. We're going to take the number of peaks minus 1 to get me the number of neighbors. So 7 minus 1 is 6. 3 minus 1 is 2. 6 minus 1 is 5. 2 minus 1 is 1. 3 minus 1 is 2. Alrighty. I'm going down the integration column, looking at the number of integration and putting that many hydrogens on a carbon. So peak A should have 1 hydrogen on a carbon, and I'm going to make sure I associate that's A. Peak B should have 2 hydrogens on a carbon, but carbons always make 4 bonds, if at all possible. B should have 2 hydrogens. C should have 2 hydrogens. D should have 6. I don't think so. D is 2 CH3s that are chemically equivalent, 2 symmetric CH3s. So we're going to do D twice, like that. And E is another CH3. Okay, then I go back and check my formula. My formula has 7 carbons. I've only represented 6 so far. My formula has 14 hydrogens. Yep, I've got all 14. And my formula has 2 oxygens. So I'm missing a carbon and 2 oxygens. What kind of functional group has a carbon and 2 oxygens? Well, how about a COO with an O like that? A carbon and 2 oxygens. That carbon cannot have any hydrogens on it because I've already got all of my hydrogens represented with earlier pieces. Whew. Now for the total assembly. If I've got this COO piece, there are 2 functional groups that have a COO piece like that, a carboxylic acid and an ester. How do I know if I have a carboxylic acid or an ester? Well, there were 2 regions in the proton NMR that you needed to know. Protons around 7 are on benzene. We ain't got that. Protons around 10 are connected to an aldehyde or a carboxylic acid. We don't have that either. So it must mean that we have an ester. So I'm going to start by knowing I'm going to have a carbon connected on that single bonded O over there. That's how I'm choosing to start this problem. Is that the right way or the only way? No, there's a lot of ways to start. That's how I'm going to start. The reason I'm starting there is I know oxygen is very electronegative. And so that's going to mean any hydrogens connected to this carbon are really far downfield. Remember, downfield means to the left. So I'm going to say hydrogens connected to peak A are on that carbon. You follow all that? You got a rewind button. So peak A represents 1 hydrogen, and there are other places to plug in. That is A. Okay? Then I visit A should have 6 neighbors. So 6 neighbors. Ooh, I see a column over here that represents 6 hydrogens. So let's do that. Well, let's put, I'm going to squish it because I don't have a lot of space, 2 CH3s next door to A. I'm going to label that D because that's how I drew this little arrow down here that A has 6 neighbors and D represents 6 hydrogens. We can cross-check. 6 hydrogens should have 1 neighbor. Oh, look, those 6 hydrogens have 1 neighbor. This half of my ester is done, but I need to plug something in on that side. Let's do it. Carbon over here. A is done, D is done, D is done, D is done. Okay? So over here, on the other side of my ester, that's also kind of near the oxygen electronegative stuff. So I bet the next carbon in line, carbon B, I bet carbon B is what's connected on this other side over here. So let me run with that and see where I get. If that takes care of carbon B, I need to check my neighbors. Carbon B has 2 hydrogen neighbors. Okay. Carbon B has 2 hydrogen neighbors, and C actually represents 2 hydrogens. So maybe B is connected to C. And there's C. All right. B needs 2 neighbors. Look, B's got 2 neighbors. C needs 5 5 neighbors. C has 2 neighbors on one side. Must mean he's got 3 neighbors on his other side over here. Anybody got a guess for what that is? Obviously, it's my only missing piece. E must be connected next. I realize this is super squished, but I hope it's still legible. E is connected next. We can double check and triple check everything. That's the nice thing about spectroscopy. There's one answer, and if you really know what you're doing, you can check and double check and triple check and be absolutely confident that you got the right answer. So E should have 2 neighboring hydrogens. E, 2 neighboring hydrogens right there. 1, 2. Whoop, whoop. The answer was pretty tough. I make it look easy when I do it. Maybe you don't think so. But often, it looks much easier when I do it than when students are working on them on their own. Be sure you spend quite a bit of time practicing NMR assembly because you'll have a few of those as graded assignments later. Oh my God, please make it stop. Yeah, we're not going to do this whole example. The only reason I pull up this example is to point out one thing. Protons around 7 are on benzene. So if I'm filling out a table about protons on benzene, I might say this is signal A. It's a shift of around 7. It has an integration of 5. What type is it? I don't know. It's real jumbly. Do you really expect me to count all of those peaks? No. In aromatic things like benzene, the number of neighbors gets real confusing. It gets real convoluted. So we're going to say the type is aromatic, and we are not worried about the number of neighboring hydrogens. Anytime you recognize a peak is around 7, just tell me it's aromatic. You're not worried about the number of neighboring hydrogens. So all of those aromatic hydrogens showed up as one lump that integrated to 5. But these aromatic hydrogens actually separate into 3 separate peaks that integrate to 2 and 1, respectively. So what? You're going to fill out the table that says the same thing. There are 5 peaks in the aromatic region around 7. Yes, I recognize that's pretty far from 7. But around 7, they're connected to an aromatic ring. I am not worried about the number of neighbors when I recognize it's aromatic. Yeah? Oh, so close. Protons on heteroatoms always show a comparatively broad signal. So they are a singlet that's a comparatively broad signal. So it's a pretty wide little singlet. Sometimes they disappear. We're not going to go into the theory of why, but it's all in your book for you to read. I'm not going to read this to you. We're done.